Hey folks, today with me is Marco Nawijn, and he's a manager of high-performance structures and material group in a large company. Marco is also involved in many laboratory tests, and he does inspections of other people, FEA analysis, and a lot of other stuff. And today we've come here to discuss something I don't think we'll agree on, and that is how much of that theoretical background you need to know to do FEA, and we'll have a friendly conversation about it, so we can both learn about what we think on this. But since Marco is my guest, I feel that it's only fair to ask first. Marco, could you tell us a bit about your background, what you do, what challenges you face, and where are you coming from? Because I feel that this might be important in the discussion. So let's start there.
Yeah. So first of all, thanks for the invitation. I think it's very nice. I'm very well. You will down the line. You will find out. But I'm very passionate about simulation, and in particular simulation, say in a quality control or certification context. So just a little bit about my background. I have a background in aerospace engineering. Worked for the National Aerospace Laboratory in the Netherlands for about 15 years. The first half was in computational mechanics and design of lightweight structures. But slowly I moved towards certification testing. First off, say, small components, but up to, say, vertical tail planes, rudders, elevators, and things like that. And the reason why I got more involved is that, say, in the last, 15 years, virtual testing, so the prediction of the test outcome has become quite important. So what you see if you do certification testing in aerospace, the guys or girls that visit the test or witness the test from the customer are the simulation guys. So when I was at the National Aerospace Laboratory, the test department found it very comfortable that also from our own side, the simulation guys were involved in the testing to, of course, assess the correlation between the data that you get out of the test and the simulation model. Okay. And I got fascinated by this because despite all the best efforts we do, me including myself, in general, there will be differences between the test and the simulation. And in my opinion, the best thing to learn from is understanding where this difference comes from. So it's typically because some details are not modeled, or there are things, say, in the test setup that are not modeled at all. Play a little bit between holes and axes, etc. So again, for 15 years, something like this, I was in computational mechanics and certification testing. Afterwards, I started my own company, mostly in the same line of work. Heavily involved in certification testing or qualification testing. But the other part of my job was, say, guiding engineering companies when they got stuck in running an analysis or didn't get the outcome they expected. Sure. And yet another part was done a lot of, say, root cause analysis of parts that failed. And always in the context where simulation has been done in the analysis or in the design phase. And what I learned from that is that in many cases it's a lack of understanding is maybe a little bit strong. But the common thread is that a misunderstanding or a lack of knowledge on the part of the finite element practitioner, let's say it like this, that missed, say, physical behavior or even finite element, the characteristics of the finite element simulation, that ultimately had a strong contribution to the failing of a part.
Okay.
So I think that's more or less. So we got into this discussion on post, which was very nice. I said it before, a very nice post. But I don't think we fully disagree, and you can always
I'm sure
about say the level of knowledge. I want a disclaimer. I'm not a specialist myself. I know pretty much about finite element analysis and know what to look for or what to look out for. But I do believe that having a proper understanding of, say, part of the mathematics or the physics behind and how finite elements are actually implemented is really beneficial for the practitioner. And
that would be like I'm very curious where this will go. Like, we haven't practiced this. Like, I'm really curious where we'll end up. And let me start by saying that I really mean it, by the way. That's also important. Like, you have one of the best experiences in FEA you can have. I feel that in FEA field there is this huge problem that if you think about the design, it's basically a toss of a coin. So you design something and you toss a coin. It either fails or it doesn't fail. So effectively, you could develop a method of designing stuff by using like tossing chicken bones in air and they fall on the ground in a random pattern, and you look at the pattern and you try to say whether the toss of a coin will be positive or negative for a given component, right? And you could literally feel that in some cases, FEA can be used this way. You just do whatever and then toss a coin. It's either okay or not, right? So imagine a situation that someone would design something with FEA that is 10 times over design. It could be way lighter, like smaller environmental impact, everything, right? But they don't know about it. The thing hasn't failed, obviously. So you could say that the analysis is a success. But what you did was something completely different. You did a test. You knew the actual outcome. So now it's not a toss of a coin. It's toss of a lot of coins that have to fall down in a certain pattern for the analysis outcome to fit the experimental testing. And suddenly this becomes way more difficult to predict what will happen. Like, effectively, a good engineer could more or less guess a toss of a coin. It will be okay or not. In like most cases, the answer would be like relatively easy to guess, so you don't even need FEA for it. And like, when you have to benchmark an analysis against the test that will really be executed, this really gives you like there is a necessity to dive deep into what you've done to find all the points that doesn't work, right? So to this, I think that your experience in it is wonderful. And I'm really curious, where do you find a way for the mathematics to impact it? Because I have to say that I did some of this, but like, to your experience, mine is very small. I just did a PhD, few tests here and there. So I'm not like, I don't have 15 years of laboratory experience behind me or anything like that. And like, I was able to find why my FEA models didn't work and benchmark them against the test I did or someone else did, and I just knew the result. So, and like, when you said that you're not an expert on FEA, I smiled, because I'm pretty certain that when it comes to like mathematics of FEA, you will beat me like with left hand. So, so maybe let's start there. Like, why do you think that knowing how because what I wonder in this discussion is the semantics of things, right? And so I would define mathematics as understanding of how the matrix operations in Solver are done, how this is implemented, and so on and so forth, right? So maybe let's start there. Like, how do you think this would impact, like, it can impact the actual FEA outcome in a way that knowing something means that you will do a good job, and not knowing this theoretical thing means that you will do a bad job? And like, I think that we'll like quickly find the limit where we like disagree with one another, so we can discuss this further.
So for me, there are two parts. So it's not, so either it affects, say, the quality of the result, and the quality. So you ask about the mathematics. So it's either, say, the quality of the result, or it allows you to quickly say debug or find. So the solver doesn't run, and you need to debug what the problem is. And for me, there are one example is, let's say the solver complains about negative pivots. And I never. Well, it's always never seen.
No. I don't know what. Oh, the pivots, you mean?
The pivots.
Yeah. Oh, okay. Sorry, I misunderstood. Yeah. Okay.
Yeah. So what I teach, try to teach, and I am also now creating some course material for linear algebra. I teach people a little bit of, say, Gaussian elimination, that you know what the pivot is, what its role is. So if the solver starts complaining about pivots or condition numbers, or that you get a feeling for what's happening. So pivots are always, okay, there is somewhere you missed a boundary condition, or there is a mechanism in your model. And I've seen so many engineers that look at the solver output and have no clue, because in the end, a solver talks to you in terms of linear algebra. It talks about decomposition. It can't do the LU decomposition or LDLT decomposition. It has a bad conditioning number. It has a negative eigenvalue and stuff like this. And for me, I would like to. For me, it's immediately obvious. Also in a model, and then I have a list in my mind. Okay, it's either so we had it with. People that try to connect two trusses, and then they get problems with rotations. So then you get over there, or you couple a truss to a beam, then you always have a mechanism, a kinematic mechanism, or you don't fully suppress the boundary conditions. So you have some kind of kinematic, and the same for. I had enough engineers that wonder why they get eigenvalues of 0. And for me, it's it's obvious, because you have a rigid body motion in your model.
And that's I got relieved because I guessed the correct answer to this.
Yeah, and again, and this is one of the things and so for me, it's more quickly debugging. So understanding the relation between, say, the practical finite element model that you built. Behind the scenes, it's always solved in terms of linear algebra. It are all matrix vector operations, and the solver talks to you in terms of linear algebra. And I try to, say, teach people in my group just enough to make sure that if there is something with a pivot or a condition number or a negative eigenvalue, stuff like this, that it immediately triggers a response.
Okay, so maybe let's firstly go into the debug, because I can honestly say that I learned nonlinear FEA with trial and error.
Yeah.
And it took me year, maybe 2 years of doing a PhD. Simply my PhD supervisor told me look, this is PhD, you need to do FEA. So I just sat in front of Abacus and clicked every button and make notes what they do until I figured it out, because back then, searching for YouTube videos was not a thing, at least not where I was at. So I think that we do agree on one thing. It's good to know what you've said. So I have to honestly say that when it comes to Gauss transformation, I have a vague idea that there is a matrix, there is like a vector maybe, and you do stuff. That's all I know. There was a name, I had a lecture, I most likely even have an A from that subject at university. Kill me. I wouldn't do Gauss transformation if my life depended on it, unless you give me access to internet in a few hours. So when you said that to understand what pivot is, I have to confess that I always thought that pivot is like rotation and the model pivots, because I've learned to associate the error with lack of boundary conditions. So I was thinking, something is not supported, so it rotates, the pivot is too big, you suck, basically, right? So, and here we enter like an interesting field, which is, do you really need to know the mathematics to be able to interpret the signs? Because to me, I don't know Gauss transformation at all, right? Like if I would have to do it, like I don't even know what pivots are. Like now I know because you just said so, but like before our conversations, I honestly didn't know that, right? That it's a mathematical thing. I literally thought that the model rotates. But at the same time, when I was debugging my model, when I saw pivots are wrong, I instantly knew that boundary conditions were wrong. And to me, the knowledge required in this particular, of course, this only works in this particular case, right? Would be, if you have pivots, your boundary conditions suck. So you don't really need to know mathematics. All you need is a conclusion. I usually use a car analogy for better or worse, but trust me, I know next to nothing about cars. But when I'm driving mine, I know where to change gears, even though if you would like give me every piece of a car separately, I'm not sure if I would even recognize a gearbox. I'm a civil engineer. I don't like cars that much. So I have no idea how it works. I kind of understand that there are like gears involved and like, some work, some don't. But like if you would have like several pieces of equipment, I'm not sure if I would recognize a gearbox. And yet when I drive, I know when to change gears, right? Yeah.
May I comment on it? Okay. Suppose your oil level is low. What I have for me, the two, if we keep in this analogy, for me, the two differences are, if you have the knowledge, you open your hood and you put in the oil in the right in the right spot.
Okay.
And what you do is say, okay, I look at everything I can put oil in, and I put it in, and I see what happens.
And yet I don't know how the gearbox works, but I do know to check the oil.
Yes.
And what I'm aiming at here is, I'm not trying to pick words. I'm very far from it. Like that's pointless exercise, really. But what I mean by this is that we live in such a complex world that at some point you have to cut off what you are willing to learn and where the limit is. And I think that we will agree on most things. I'm absolutely certain about it. After this length of our conversation, what we won't agree maybe on is where is the cutoff of what you should learn and should not learn. Because to me, it's not a problem of should I know it. I mean, like, come on, if you give me like free knowledge without effort, I'm taking it, whatever the knowledge is about. Like, it's always better to know than not to know. That's obvious, right? But we have a limited effort we can spend on learning in our lifetime. So, and way too much to learn everything in our life. So we have to be very selective on what we learn and what we choose not to learn, because we believe that the benefit of learning it's not good. So I will not defend the stance that it's a wasted effort to learn FEA mathematics. That would be stupid. Like if you would give me a peel or like a matrix plug that teaches me all the algebra in the solver, geez, I'm taking it, man. Like obviously, but I know also that to understand it realistically, it would be a few years of effort to learn all the mathematics. And like, I never liked mathematics that much, right? So in those few years, I could learn something else that might be more useful to me. And if I can switch few years of mathematics learning to a few, let's call them superstitions, like before you go to a long road, check your oil and, check the gears when you're driving, right? I don't need to understand how this works and why, as long as I am following the superstitions that I do not understand, but I am following them, thing is functional, right? To this extent, if my laptop would broke, I wouldn't even try to like open it. I would just, take it to the store and say like, do the thing, right? And the funny thing is that the guys there most likely will just exchange part to new ones until it starts working again, because they wouldn't be able to fix my graphic card either. Like there are very few people who would actually be able to fix a broken part, right? So I think that to this argument, when we are talking about like how the solver works, right? I completely understand that it's, especially in debugging, it's very good to know the spells the solver gives you, right? As you said, it speaks in algebra, right? But if you don't understand it and yet you learn, I see pivot, I need boundary conditions, I see this, I need that, I see this, I need that, only the conclusions. Maybe that's enough.
But the point is, it took you, it's a balance. So it took you some time to understand if the solver says this. I don't know exactly what it says, but if you start tweaking boundary conditions, the solver stops complaining. For me,
this happens
it's also, but there are many people, engineers, that spend hours and hours more or less randomly doing stuff because they don't really comprehend what the solver is telling them. And that's my point. Not only it will typically not make or break your result, because in general, if it starts complaining, it won't solve the system. And on the other hand, I've actually in practice, are you aware of param bailout in Nastran?
Yeah. You can calculate wild stuff.
Yeah, but I've seen people run real analysis with param bailout set, and that's and that's really a debugging statement. And what the solver is doing, it keeps, say, removing rows or fixing degrees of freedom until it finds a system that it can solve, and that's really a debugging statement. And I've seen plenty of engineers that just run with param bailout because the solver never complains. And they say, okay.
Well, from their perspective, it works. So to those of you who are not Nastran geeks, param bailout is the thing that you enter to calculate a model that won't run, just so you see on your screen something in hope that what you see will help you to find why the model didn't run.
Yeah. Exactly. So for me, again, back to the topic, for me, and there are also many engineers that don't look at the solver output. Don't look at because it typically has warnings on say, element shape.
Especially when you do like
and stuff like that. And so I've once. Also, that's already 10 years ago. So I think 10 years ago, we had to really deliver a finite element model for application in a real space, part of a space vehicle. And really, the quality control documents, it was something like 30 pages. So with all the checks that we needed to do before we are even allowed to submit the model, and those were all on the number of triangular elements, in combination with the type of analysis that you do. If you have a triangle, what's the location? It's in the location where you want to do compute stresses, at least stresses for reporting or critical stresses, or do you use it in the part where you have plasticity or not? And we had lots and lots and lots of tests like that. And so then it's really, you need to study what the solver tells you.
Well, I think, correct me if I'm wrong, I think that we will both agree that it's important to understand the conclusions of the mathematics to operate and debug the models, right?
Yeah.
So what I think we differ in this case is how to get to the conclusions, because obviously you can learn all the solver mathematics and derive the conclusions, or you can do, like in my case, a trial and error, and after seeing all the error messages in FEA, you kind of know which one is which one, and you simply get the knowledge practically, right? And of course, nowadays there's a third option. You can ask someone, even online, although, kids, we are random guys from internet, so be careful with our opinions. But you can ask somebody to give you the superstitions, right? And then you haven't done the years of testing, you haven't done the years of learning mathematics, you just trust the source of knowledge that gives you the conclusions, right? And of course, it's either of the three approaches would have drawbacks. Learning mathematics make your head hurt if you're me. Doing this by trial and error requires you to doing a PhD in a stressful situation, because otherwise there is no way you will motivate yourself through 2 years of trial and error stuff. It just doesn't happen normally. And the third one is, when you have a source of knowledge and that source is wrong, you will never know. Because you just you follow the superstition realistically, right? So each of those approaches have problems. So in some sense, the question would be, which one of those three would be the best? And I think that it will come down to a personal choice of what you are willing to suffer, let's say. So you can either risk trusting someone or like spend energy with trial and error or learning, right? Do you think that I'm getting somewhere close to what would we be able to agree on?
Yeah, I think so. And I think I'm biased by my background.
So, we all are.
Yeah, and in particular, because I've worked so much in certification and qualification programs where the guy sitting in front of you tries to drive a nail in your finger. And so I really, and also for the insurance cases, I've done work for insurance cases. And you really need to more or less officially state whether or not an analysis is right or wrong. Or
I don't envy.
it gives myself comfort that I fully understand, or at least to a level that is acceptable, say, for the type of questions that I need to answer. But I'm pretty confident in my knowledge, and that's why I don't mind entering these kind of discussions with certification bodies or and again, I've seen in practice, also in insurance cases, that lack of the thing I really hate in finite element analysis is the notion of failure criteria.
Oh, okay.
And why? Because people that read finite elements report and the finite element report states failure criteria believe that is actually, say the level of load or whatever that makes the structure fail, which is insane in some regard, because I've seen the wrong results from this. And so for me, I find it important, at least, that the people in my group have a proper understanding also for digesting documentation. There are, I think, there are many engineers that struggle, for example, with tensor notation. What is a tensor and how does it work? And then, but if you start looking and do more complex analysis, and you want to look into the theory manual of, say, ANSYS or Abacus.
Oh yeah.
And you start looking in, say, the constitutive equations. It always starts with tensor notation and with and so I also try, at least for the people that are interested, try to explain a little bit that it's not black magic and that it's not too difficult to understand, but it takes a little bit of time. But it makes either reading papers. If you do I'm now also I'm moving now a little bit in the company to computational fluid dynamics, which I've done in the past, nice. but it's been a little while. So I'm also trying to look up reference problems that are published, etc. But also digesting and understanding a paper. Yeah, it helps if you have a little bit of theoretical background. Yes. Because otherwise, it's very difficult to understand, and it's a very useful for me. And the first thing I do if I do something new for me, not in general, but if you do I first try to find a paper that already done the type of analysis, and I try to just redo it and see if I come up with the same answer, or I take a benchmark problem, etc. And it's particularly in this kind of context that I believe it helps if you have a little bit more theoretical background, because it makes documentation and published papers easier to more accessible.
Okay, so let me maybe comment on this. I feel that you're touching on a very important subject, and without a doubt, to me, reading a solver manual is a torture. I can do it more or less, but I admit that I skip equations much of the time. So I'm searching what which parameter does, how they operate, like within what boundary the values are reasonable. And this is what I'm searching in manuals. But if you would slap only the equations of the manual on me, I'm just like, just kill me already. Don't torture me beforehand, right? So to this end, I absolutely agree with you that knowing mathematics when you want to read this stuff is a valid skill. And when it goes to science articles, I actually written a few myself when I was back at university. Now I'm like, the thing with that is that when I started blogging, my employee, who was a PhD researcher at the time, told me that I need to write a blog in a language you don't like write scientific materials in. It's a skill that is boldened in you. Or at university, they kind of expect you to use 20-word sentences, and each word on average should have at least 5 syllables and stuff like that, right? It's like a way, right? It's like a poetry of science, but a rather crude one, right? And I would say that it's true that knowing mathematics and like having the ability to read those texts helps, but at the same time, one could say that if scientists would wrote easier to understand articles, everybody would be better off. Right? Because I know on the same field, I studied shell buckling for like 10 years. In the same field, there are professors who I can read work of like a book. It's enjoyable. I know what they did and so on. And even though I have a PhD in a field, there are guys who I would never understand. I just reading this and like, I'm crying blood. And then one could say, okay, so am I too stupid? Clearly I am, because if I would be smart enough to read that difficult text and understand them, things would be better. But at the same time, what's the difference between those two authors? And I would say that one of them tried for me to write in a way I would understand. So he cared for me to understand him. And I feel that mathematics, to a certain extent, is a defense mechanism against people writing books they don't care you understand. But it would be so much better to expect from writers to write books you actually would understand. And then, like, as you know, I write a blog, and I've got hundreds, if not thousands of emails from people all over the world telling me, man, if I only had a teacher like that at university who can speak about difficult things in a way I can actually understand, right? And oftentimes nobody cares because the science is constructed in a way that you need to write a very, very complicated book, which is clearly scientific, and then you will get a professor, right? So sometimes the goal is to complicate a simple matter so much that it becomes worthy of science. And I think that actual science could be done the other way around, right? So while I completely understand, and I absolutely agree with you, that knowing mathematics would help, even like it would definitely help me when I was learning shell buckling, right? But also when you said that when this is so cool because you have this skill, your approach to doing something kind of new would be to find a scientific article and reproduce it. Mine would be to reach out to people who already did that and talk with them. Because then if someone is good at what they do, I know they know the answers, and it's the asking the questions that I can ask and dumbing things down for myself. Then I can understand how to do this properly. And I think that for better or worse, much of like the creation of content in the world is done by people who don't care, because it's their scientific career or super accurate mathematics they sell in a solver that is the dominant thing. And, you know, if you would read a manual to an online service that gives you an SEO advantage of your website, they have like 3-minute YouTube video and 10 bullet points. And this is all you need to know. And compare that, and the service is $10, right?
I think we are not that far apart in because I'm not writing. I don't take the source code and start writing down the solver myself. And so I think we mostly agree on the only thing I have, because what you say, the 10 bullet points are for me maybe 60 slides on linear algebra.
And compare this to 2,000 pages of Abacus manual, eh?
Yeah, and for me there are the I always, for example, and so shell buckling is also a nice example. What do you do when there is a mode jump of your solver doesn't converge anymore? You run an implicit solver and it doesn't converge anymore.
Oh, you can do arc length though, and then it would, unless I don't understand what you're talking about.
Yeah, but I can give you. I really, because that's what I do. I can give you. I don't know. A 20 element model, and your solver will not converge.
Okay, that's cool.
Rectangular plate. It's a rectangular plate problem, and you can especially. I've done it a few times with engineers in my group, and also at the National Aerospace Board, and it's actually a real observed phenomena. And what you can do if you have a rectangular plate in compression, 20 elements. I don't know, something like this. But you don't have simply support boundary conditions on both ends, but a torsional constraint along the sides. And what you can do, you can tweak the torsional constraints in such a way that the first two eigenvalues are the same, but they have different modes.
Okay.
And the nice thing is, because this is not an artificial dreamed up thing, we actually saw it in because I did a lot of buckling tests, really a lot, and we saw it really on a real aircraft structure.
Oh, that's so cool.
Because what we saw is that we did a test. It was a compression test, and already I can't disclose the customer, but the finite element, and normally we would always get the pre and post buckling predictions. And for this particular test, I think we did 20 tests, something like this for them. And for this test, we didn't get the data. And I asked them, why don't we have the data? Because the solver wouldn't converge. I said, okay. And then I was at the National Aerospace Laboratory, so that triggers my my research nerves. So I asked him for the model. And that was specifically a model where a real structure where the first and second eigenvalue were nearly the same.
Okay.
And then we started the testing, and we had a digital image correlation system, so we can have a full field digital image correlation system, so you can look at the buckling fields. And throughout the whole test, to deep in the buckling field, there were 4 or 5 half waves, and the pattern was continuously shifting up to really deep in the post buckling field. And then again, that of course it helps. I did these type of analysis further. So if you at some point see that the solver doesn't converge, that this immediately triggers these kind of things. Is it two solutions pretty close to each other?
I've only seen something like this when arc length gets dumb on you. Yeah. Like when you have a classical buckling, it goes sharp to the bifurcation and almost the same way back, right?
Yeah.
And when you do arc length, you can actually miss the post-critical path and simply get back to the 0 point. Because
arc length and Newton-Raphson, if you have a snapback. Snapback is like this.
Yeah.
With Newton-Raphson, you only go
like you jump.
Arc length, you can go down.
So, like, I think that with those cases, though, when you animate the outcome as an engineer, you will kind of notice that something happened, right? Like in the case of Newton-Raphson, you would clearly see that something is happening, and suddenly, bam, you're in a different place, right? You will instantly know that something is off. But the problem you described with those two modes being so close to one another, it's fascinating. I must say that I've never seen something like that, but I don't think that I would be able to solve it in this case. So in those particular cases, I give you this, that understanding the mathematics of the solver might be the only way. I'm sure that you could trial and error through this at some point, but realistically speaking, if you get something like that, that would be so weird. And I'm not sure if I would solve it. So to this extent, that's true. But what I also have to say is that that's a buckling problem that kind of is on the outskirts of what I know, and I have a PhD in stability, which clearly shows that it's like a very fringe case that's like so super specific that would literally require someone with a scientific background of doing just that to solve it, right? And this is most likely why I'm dealing with stability for so many years, and I haven't encountered it yet. Although this is not an argument that it doesn't exist. It only shows that if someone knows the math, that person has the tools to deal with the problem at hand, and I wouldn't have those tools. So to this, that would be a very good idea. I've never thought about things like that because that's so bizarre, you know? Like if you think of like, what's the chance of something like that? And yet it happened, and you saw it like in your
like, for me, there are other things. And so how can you say assess whether or not the grid density is so you have enough elements to capture the proper stress response?
Well, first of all, you can do mesh convergence study. This doesn't require understanding how this works. All you need to do is like, there is a superstition that every time you're not sure about the outcome, do mesh convergence and see what happens, right? And then the superstition says that if the stress doesn't converge and you have a fatigue problem, then you're in very big trouble, right? and then there are like International Institute of Welding recommendations or whatnot to deal with this problem like in a reasonable way, right? But you wouldn't have necessarily to understand why, but there is a functional solution to this problem, right? To the extent, like now I'm struggling with something else, and that is that plastic strains may not converge to a reasonably small value, and then many codes provide a limit of the plastic strains in your model should not be higher than whatever, and realistically some of the details would have a geometry that would lead to plastic strains that are like 50% or something, right? And yet those things exist, they function, and nothing happened, right? And this is something I'm trying to cope with. But I also don't think that would be the problem, like that this problem is solvable with mathematics. It's more the problem of how do we measure the things that cause failure, and how do we express the failure in terms of an outcome in some sense, you know? Like that understanding how the plasticity algorithm in my FEA works, like that wouldn't help me solving this problem at all, because it's not an FEA problem in some sense. It's a way more.
But what about, say, and again, it's people that do finite element analysis at some point, of course, learn because it's something you build. But and what is still, say, in the singularity, how to get a proper stress? But what do you report in terms of a stress value?
Well, first of all,
and that's where typically also the mesh. If you do automated mesh convergence, then you're in a singularity. You have a problem because it starts. The stress is getting higher, and so for me, I see a lot of, and it's not. I don't claim that it's always an easy answer, but again, having a little bit of, say, the theoretical knowledge helps you understanding if you. You have the same. I've seen structures completely over-dimensioned. The whole model is a dark blue, and there is one tiny little red spot somewhere.
Oh yeah, of course, yeah. And I've seen things like, you know, complex geometry with 10 elements, like literally not representing the shape, right? And people are, I have this too high stress. Like if you would start a blog, you would be surprised how many emails like that you start.
No, and that's my so, and maybe I'm insecure on myself. It's also so I really like diving in a little bit into the theory and understanding if I can explain the behavior, say, I see, or if I can trust the results I get, or if I and for me, I really I like to have a little bit on background, in particular when the analysis start getting a little bit more complicated. I have this list in my mind. So what, and you do it. I think you do the same thing. What could be wrong? So if I always ask myself the question, how accurate is the result? And then you immediately ask, okay, what could go wrong? element
Sure,
type,
sure.
normals, element shape, and call.
We actually have a checklist.
Yes, you have a checklist and say, okay, and that makes me feel comfortable that if I at some point generate a report that you can trust the values. And I fully understand there are lots of finite element analysis that are more or less, I don't know, that the actual quantitative value is of the accuracy. If you're 20 or 30% wrong, you still will never have a problem because because you need to compare it to Eurocode or whatever, and that is
Sure.
and you have lots of safety everywhere. But say you get into the aerospace, then you get in trouble because that costs weight, and so again, I think we are pretty much on the same page. I would, and in my opinion, I would like a little bit more theory, and then probably what you feel comfortable with or what you would propose. But I'm not advocating that you take 6 PhDs, say one in linear algebra, one in plasticity, whatever. But having a little bit of background, and maybe a little bit, in particular when you need to digest or access papers or documentation, etc.
Yeah.
Then I think it's worthwhile, or even debugging complex models. It's worthwhile having this theoretical background.
Okay, let me ask you this though. Do you think, because to me, I think that like somewhere in me, I have enough brain cells to learn how the linear FEA solver works. Like, all the, like recently I co-authored an article with a friend on a blog about it. And I've read it and I kind of understood it, and to the point that I was actually able to draw some charts and explain it a bit deeper. So I kind of like, I'm fuzzy, but maybe okay on this, right? But when it comes to nonlinear stuff, I have a friend who did a PhD on making some random name of a person who's author of a random kind of solver thing, and he made a PhD on how to make the solver more efficient. And I sit in his defense of his thesis, and I didn't understand a single thing. Like seriously, man. Like I just sit there and I was like, okay, like sure, why not, right? I've seen more boring movies in my life, but realistically, when it comes to nonlinear things, I'm pretty confident that at this stage, I am using a solver that is so bizarrely complex in its nature that even if I try, I wouldn't be able to understand it, because there is just too much of everything in it nowadays. And that when we talk about background, it's easy to say, oh, I understand that, like, the pivots that would come from linear FEA. I understand that nonlinear would show the same errors, but like, you can relate to this in a rather simple environment, let's say, right? But at some level, well, realistically, day to day, we're making analyses that are way more complex than a simple linear stress case. And then understanding the solver then I don't think that it's within my living time learning capacity, that it's just too much of everything to learn it, right? So then learning the mathematics of linear FEA would be like a dumbed down substitute of what you're actually doing, right? And is there perhaps a trap there that it gives you a false security feeling that, oh, I understand how it works, while in fact, I'm not saying that people who understand mathematics think way too much about themselves. That's not the claim. But what I can say honestly is that I have a certain, I don't want to say fear, maybe respect to the solver as an entity that is beyond me. And I'm always cautious when I look at outcomes, and I always think like, is the solver lying to me this time? It's like asking a fantasy oracle in some sense. She will always tell you the truth, but this may not be the truth you want to hear, right? So, and when you have this false sense of security, it can actually derail your analysis, because I can personally tell you that I've been in situations like this. As you know, I like to discuss this. And I've been in situations where people did stupid analysis, like really stupid, wrongly supported, bad assumptions, like, the stupid design, right? But they would argue from a base point of, I have a PhD in numerical simulation. What do you know, you idiot, right? And then how would you argue with someone like that who believes that understanding mathematics somehow miraculously make you a designer? Because I think that's like a flip side of this problem, right?
Well, I can answer to that. I'm completely on the opposite side of the spectrum. I love mathematics. I love computational mechanics. But the first question I always ask to a finite element, say specialist, is how many testing or how many have you done in your life, and how much, say, actual manufacturing? Because in the end, we live in a perfect FEA world. Yeah. While then you go into the factory and see what they, for example, with composites, what they really do. Because no matter say the complexity of the model in your FEA model, you can always, and the fibers will always nicely run continuous, and then the factory they start cutting and doing stuff like that. So for me, if I need to judge, say, a finite element model, one of the first questions I ask: how often do they visit a factory? How often have they done testing, etc.? If the answer is none, I really don't care if you have 10 PhDs, but I don't trust your model. Okay. Because for me, FEA models come from, say, of course, an understanding of what you do, an understanding of the finite element process of a method itself, but a large contribution comes from understanding what's the difference between your model and reality. And for me, that's far more important than that you fully understand the physics.
Okay.
For me, really, the theory, and so why I like having a theoretical knowledge is more because it's on, say, more on. I can more quickly go through my checklist. If I need to ask myself what's the quality of the result, I can more quickly run through the checklist because I have an understanding, and I know for sure if I do this type of analysis, or if I've selected this option, I know from a theoretical background, or I've checked it already, that I can easily check off done. And again, for me, it's indeed in making the FE process more efficient. So for debugging, I really like it. I have nothing with. I like studying. I have an interest in physics and in computational fluid dynamics. So if my girlfriend is watching Grey's Anatomy, I'm reading, I don't know, theoretical aerodynamics or something like this.
And I think that really helps.
I'm not a specialist at all, but I find it so, I don't know, fascinating that the complexity that you see in nature, that you can so beautifully capture it with mathematics and then practically solve it with the numerical finite element of numerical methods, whatever you use.
Sure. That's beautiful. I shared the passion. Like, I wouldn't read a book. I would most likely figure out a stupid problem and try to model it and see what happens. Yeah. So I think that we differ in like temperament of our characters, that you would rather learn some theoretical stuff and then implement it. And I would just, tweak around and see what happens. And then I will kind of have a vague idea of what's going on. So
you will never hear me that one is better or worse than the other. It's again the bias from the background that you have. I really had to state something about accuracy and why I believe a result is good. And then at some point it helps if you say, okay, theory. If you don't believe me, there is a paper that's published. Have fun. Look at that. That's the truth. And
sure.
sometimes that helps.
Okay, so maybe the last thing I want to touch on would be something like this. I don't know how this works at your end, but here, if you would like to study FEA at university as a subject, you would basically have few lectures on mathematics, a lot of transformations, and basically you will do the FEA math, however you wish to call it, right? And then when it comes to practical applications, the practical application would be, let's solve this rectangle with 20 elements, and please apply this boundary condition here, this boundary condition here, that load there, without any implication how this would work in real life, but rather let's, instead of doing the matrix, let's allow the solver to do the matrix for you. You know, this would be the practical thing. If you would buy 20 random FEA books, I'm willing to bet that 70% of pages contain at least one equation. And I would be willing to bet that 50% of those pages contain a long equation I wouldn't understand. So reading such a book is a freaking nightmare. When I was starting, somebody recommended a Crisfield Volume 2 to me. You know, Łukasz, you're doing nonlinear. You're doing nonlinear FEA, so like read it, right? I lost it like 10 pages, and I just like throw it away. It's somewhere here, right? So what I'm aiming at is that my maybe too strong stance on you don't need the mathematics comes as my real feel that most people do not understand that this is way less important, that it's being portrayed. Like if you want to learn FEA in any setting whatsoever, the mathematics will be literally one of the only things you will be taught, either on university or from the books. And people get this weird notion that since I know the mathematics, I must be good, right? And to this, to oppose this, I would have a very radical stance by saying, "Oh no, you don't need mathematics. That's actually not how the game is played." Right. And in this conversation, we clearly have common things. And I have to admit that I start to think that actually mathematics to people with character like yours and not like mine would actually be like a more suiting vehicle to learn the superstitions without trusting someone external to be the source of the superstitions you wish to follow. Like if you want to have your own rules, you can either like die hard, try them out and test them, or learn mathematics. And maybe to some people, the mathematics is the better way to go. Right. And thanks to our today conversation, I actually start to think, because, you know, I never met someone like that, that would actually enjoy this. So that's so cool. Right. But at the same time, I get a feeling that the mathematics is sold to everybody involved at a way too high price of importance. And that actually it's, as you said, it's understanding how things work, the physics behind what it was, like what you're doing, like why boundary conditions, why loads, what will go wrong in manufacturing and in real life. Like those things actually would be so much more important than understanding mathematics, right? So I would say that it would be more worthwhile to, instead of read mathematical books, read books on how to manufacture stuff, what can go wrong, learn the physics behind, and so on, right? So that would be my claim, I guess, that it may not be as radical as I thought, but realistically speaking, it's like we put in engineering training way too much emphasis on mathematics, ignoring the more important things. Please concentrate on important things, right? So what would you say to this? Like, would you agree with me on this?
Yeah, for me, and it's not what you intend, I know, but for me, it's a little bit, you have to choose either one or the other. While my thing is, it's a balance.
Okay.
So, and if do you think I fully understand Crisfield Volume 2? No, I don't.
Oh no, like I think that Crisfield fully understands.
When I'm retired, maybe I will give it a try. But still, I believe Crisfield Volume 1 is more comprehensible. And even I don't recommend everybody to be fully confident on that content. And for me, there are a few things that you always have. Things like, even if it's terminology, what is a deformation gradient? Well, you see it everywhere. If you start reading papers on constitutive models, the concept is really simple. It's really simple. If you had a little bit of linear algebra, how they decompose a matrix, it's really simple, and you start seeing connections. So it's, for me. Do I recommend everybody to know every detail? No, I don't. But again, for the superstition that you talk about, I have this because I'm not an expert even in mathematics or the theory, but I have a very good superstition on. I can't write everything. So if you now ask me, write a book about linear algebra, and then I would say, ooh, okay. Or on nonlinear finite element analysis, and even, ooh, okay. But if I read stuff presented by others, I can pretty good, and I can play with it a little bit, say, in my mind if I need it, if I need to do it, and I can look it up very quickly because. And they say, okay, I know I've done something like this before, or I have this paper that has the details, and then I grab the reference and do it. It's not that I know everything by heart. So what I effectively agree is with that for me, the most of the finite element practitioners are far too theoretical. And they build models that are far away from what happens in reality. And in particular with composites, or in particular when kinematics is involved, I really recommend that people make sure you understand reality and where your model differs from reality.
Okay. So I think that by this, we could agree, maybe, so correct me if I'm wrong, that if there is a spectrum of what you need to know, we would both agree that more of it would be practical things like understanding engineering concepts, how to support your model, the practical things, not necessarily related to theory. And where we differ is, let's say that I would say that you only need 10%, if all you know is 100%, it's sufficient to have 10% of it to be the theory, because I wouldn't even call my FEA theory knowledge. I would say I was very particular calling this superstition, mostly because I'm fully aware that somewhere out there's a professor who looks now at the YouTube video and thinks he's such an idiot. He doesn't understand how this whatever equation works, and he dares to speak publicly about FEA, right? So I'm flat out saying, no, this is just a superstition I'm following, and it's okay. I feel good with this, right? So I would say that knowing the superstitions might be enough. And maybe where we differ is how big the percentage of theory in the total thing should be. And I would say it's a small, maybe 10%. And you would say, maybe let's make it 25, right? And this is where we would differ. But essentially, we would agree that the majority, and I won't say vast majority because, I will ask you about the percent in a second. But the majority of the things you should know is practically oriented. And sadly, nowadays, most people, when they do FEA, they have the majority of mathematical knowledge with very little practical knowledge, which is the opposite of what we both would agree on, right? Yeah. Do you think that I'm correct here?
Yes, fully.
Okay, awesome. So to wrap it up, I will try to do a summary from the top of my head. If people watch closely, they would notice that at the beginning I was making notes, and then I just got sucked into talking with you, and I stopped. So it's summing up an hour of conversation from memory. Let's go. So I would say that we would agree that when you do and please be careful. And if I say anything you don't agree with, instantly interrupt me. So I think that we would agree that when you do FEA, the vast majority of what is important comes from understanding how physics work, how your model works, what you want to model, how it will be done, the practical things that would be important regardless if you do FEA or not. If you are using other methods of design, all this knowledge is still as important. It has nothing to do with FEA whatsoever. It's an engineering knowledge that you need to bring to the table to do the FEA. And then I would also say that there is a portion of practical knowledge, let's call it superstition, that, you need to have a nice mesh, and maybe you don't really understand how the nice mesh look like, but as long as someone told you how it looks like and he was right, the nice mesh is good. You need that there is a mesh convergence, singularity problems, what people like, that you need to check boundary conditions and don't calculate your model with bailout on, things like that, right? You need to know them. And those may be derived from learning FEA theory, or they might be like, trial and error. Someone can tell you how to do this kind of thing. And then I don't necessarily feel this, but I feel that you do, that there is a portion of the knowledge, like a theoretical knowledge, that just makes your life easier when you do FEA. Like you clearly understand more of the mathematics than I do, and this would help you debug the models, for instance, or like in some very complex cases like this Coulomb eigenvalue problem, like this would come in play, which gives you a clear advantage over me in this regard. So we could argue, of course, how much effort you could put into learning this that helps you from time to time in certain aspects, right? But in general, that would constitute of what would be smart to learn about FEA. And like, would you say that it would be wise in this case when you're learning FEA to use, 6 hours of your time to learn practical things, 2 hours to learn the superstition, talks with people who already did FEA, learn from them and maybe try some stuff, and then like 2 hours to learn theory because it's good to know something, right? Yeah. Would you think that that would be a good idea?
Yeah, in terms of percentages, I agree, and I thought you were more on the 0% theory. No. I would say I'm more on the 20%, something like this.
Okay, like I'm closer to 0 than 20. That's for sure.
Yeah. And for me, and that's I think the whole between quotes debate. So I'm recommending moving a little bit towards the 20%. Then for me, still 50% is practical knowledge, and the rest is really the understanding, but from a practical point of view, understanding the way you need to model. That's something you build up over the years, and of course you can follow the tutorials and the courses that NGIS or Abacus, whatever provider what you provide is and again, so I'm and that's also the comment, but go back to where we started. So the comment I had was I think I made a comment like it was dumbed down a little bit too much, and for me I agree with the emphasis on it's a little bit too much, but not that far away from what I would recommend. I would never recommend everybody to really dive into all the theory to the end, but diving a little bit under the hood would be is something I do recommend, and also ask for the people in my group.
So I would do a risky thing, and I will do this. Let's say that my percentages would be something like 65% would be the engineering knowledge not related to FEA at all. Yeah. So that's 65. Then I would say 30 would be the superstitions. Make a nice mesh, boundary conditions, like things you have to understand. Although the boundary conditions is kind of like in the 65 too, because you need to understand how this works in real life. So it's not. And then the remaining 5, it's always nice to know few terms that are theoretical. So if someone asks you a difficult question, you at least understand it. So let's say that would be my proportion. So your, if I recall, was like 50% of the engineering stuff. Yes. Then it was like 20% of theory and 30% of this practical things, right? So in the end, I can say that at the university, I don't know if you would agree, but to an extent, I'm aware of it. I would say that the universities propose like 80% of theory and then 20% of superstition without like the practical thing how this works. And I think that we both would agree that this is actually a problem. And while it might seem that we differ a lot when we discuss the theory, because I'm like 5%, you're at 20, so clearly I'm 4 times more against the theory than you are. Realistically speaking, we are on the same side of the conflict from like, if there is even a conflict to what FEA is, to how FEA is presented to people, right? Because the emphasis on theory is too high. And would you say it's a fair summary?
More than fair summary. So
man.
Yeah.
We did
So
it.
I think again, we don't differ too much in this. And
But like I did learn about this double eigenvalue thing, and man, like I will think on it. You can be sure about it. Like so, I'm always happy to have those conversations because, Marco, you really made me realize that I was opposing mathematics so vigorously, mostly as in opposition to universities, while in fact my position on it might be not perfect to people like you who actually would choose learning the mathematics, understanding that it may not be the most important thing, but it's still fun and it pushes me forward and it will help from time to time to be more efficient, instead of doing like my let's tinker and see what happens style. And like this conversation really showed me that this is the way. And I'm so grateful to you that you sacrificed your valuable time to talk to me about it, and that we can share this conversation with others. And I hope that they will enjoy it. So, Marco, thank you so much for joining me. I really, really appreciate
You're really welcome.
And
I enjoyed it myself. So it was really nice.
Thank you. So, folks, if you have any questions, you can leave them down in the comments below. And, have a wonderful day and see you around.